Okay, so today what we're going to be doing is simplifying radicals. So radicals, in this lesson, we're only going to be dealing with square roots. So again, here's a screenshot of your textbook. Again, you can always read through the textbook. Sometimes that might provide a better explanation. Okay, so here's our first example. Now, all of the examples today are going to be not perfect squares. So really what we need to do here is figure out two numbers that are going to multiply to give me the number under the square root, and then I'm going to keep breaking it down. Now, some of you are going to be really good at coming up with the factors of 28, and if you can find a big perfect square that's a factor, you could jump right to the answer. And this is what I mean by that. So for example, let's say, and you can do this more than one way. So let's say I decided I'm going to start my factor tree by saying that the two numbers that'll multiply to give me a 28 are going to be 2 times 14. Now, from this point, none of these are perfect squares, so I need to keep going until all of my factors are prime numbers. So I would bring down the 2, and I'd factor the 14 still. 2 times 7. Now, all of these numbers are still under the square root. Now, once you break your number down to prime numbers, we look to make pairs. So notice you have a pair of 2's. When you make a pair of numbers, that is actually a perfect square because 2 times 2 is 4, and the square root of 4 is 2. So when you make a pair of numbers, you pull them out, and only one number comes out of the square root because 2 times 2 is 4, square root of 4 is 2. The 7 doesn't have anybody to pair up with, so that number stays under the radical. And that would be 28 in simplest radical form. Now, for those of you who are good, who really know your factors fast, and have memorized that the perfect squares are 1, 4, 9, 16, 25, 36, if you can find two numbers that are going to, one of them, be a perfect square, then you really don't have to do the whole tree. I could just square root the 4 right here and get 2 radical 7. So if you can come up with a factor that's a perfect square, you can square root it and pull it out. Next one is 48. Now, 48 has a whole bunch of different ways that I can multiply to get a 48. 2 times 24, 3 times 16, 4 times 12, 6 times 8. Doesn't matter what you start with. Now, if I would start with 16 times 3, then I could go right to my answer and get 4 radical 3 because the square root of 16 is 4 and I can't find the square root of 3. Now, again, let's say you didn't realize that and you just kept breaking it down till it's prime. It works also. So keep breaking it down till you get all prime numbers. And then again, we're looking for pairs. So notice you have a pair of 2's and another pair of 2's. So as soon as you make a pair, one of the pair comes out. Anything else that does not pair up stays underneath. Everything that you paired up that comes out, multiply back together. And you get 4 radical 3. Now, if more than one number remains under the radical that doesn't pair, you also multiply that back. Now, it wouldn't have mattered if I would have started my factors with, say, 6 times 8. Because again, remember, you're breaking this down until it's prime. So 2, 3, 2, 2, 2. These are all under the square root. And again, pair 2's. These 2 pair up. So again, one of the pair comes out, each of the pairs, and then the 3 stays underneath. So either way, doesn't matter what you start your tree with. Because again, for some of you, you're going to need to break it down to prime. For others of you, you're going to be able to automatically see those perfect squares that are hiding. One. Now, notice we just did 48. So we already saw that 48, this part of it, was for square root 3. Now, notice this problem has a 2 out front. So I need to take whatever comes out of the square root and multiply it by what's already outside. So the 2 is already out there, the 4 came out, multiply it, and my final answer here is 8 square root 3. For the 645, so here again, we're going to only factor what's under the square root. So two numbers that will multiply to give me 45 are 9 times 5. And again, if you realize 9's a perfect square, square root it, and you get 3 radical 3. However, if you don't realize that, keep breaking it down till it's prime. You got a pair of 3's. A 3 comes out. You already had a 6 out there. The 5 didn't pair. He stays behind. And then the 3 that comes out multiplies with that 6. And final answer here is 18 square root 5. Everybody good so far? All right. 75. Again, it's not a perfect square. Now, for me, when I see 75, I think 25 times 3. I think about 3/4. But for some reason, students always tell me that the factors of 75 are 5 times 15. So let's go with that. Doesn't really matter. I could have done it either way. So 5 times 15, break it down till it's prime. So now I got a pair of 5's. One of the 5's comes out. The 3 stays behind. Multiply that 5 that came out with the 14, and you get 70 square root 3. So again, if I would have done 25 times 3, again, 5 and 5, the 3 comes down, pair of 5's, it comes out to the 14, and the radical 3 stays underneath. Either way, it doesn't matter what you start with. You're always going to get the same simplified radical. Let's try another one. 125. Again, I like those quarters. I see this number and I think, oh, I know how many quarters that is. That's 5. So I would break my 125 into 25 times 5. And again, break the 25. It's 5 times 5. And again, look for your pairs. Got a pair of 5's. So one of those 5's comes out to the 10. This 5 doesn't have a pair. He stays underneath. So 50 radical 5. 600. This one's got a bunch of different ways. Okay, I'm going to do 600. I'm going to break it into 6 times 100. Okay, you could have done 2 times 300. Again, it doesn't matter what you're going to start with. So let's do 6 times 100. So then I could do 2 times 3, 10 times 10. And again, as soon as you see you have 2 10's, know that 10's coming out. Or if you realize that 100 is a perfect square, you square root it. But again, let's keep going, just so we can practice getting all the way down to prime. And now we look for our pairs. So I have a pair of 5's. Oops, maybe I should just highlight. Let's do the pair of 5's. So a 5 comes out. And we also had the 5 out there already. Then I got a pair of 2's. So a 2 comes out. And then nothing to pair with this 3 and nothing to pair with this other 2. So those 2 that don't have a pair, I'm going to multiply them back. And now I'm going to multiply 5 times 5 is 25 times the 2 is 50. So 50 square root 6. Good? Now again, you could have just done this. 5, break the 600 into 6 times 100. Square root the 100 to a 10. Leave the radical 6 there, and then just multiply these two. 50 radical 6. So for those of you who are going to catch those perfect squares, take care of it. Square root it, pull it out, put it to the side. So that is simplifying radicals. Now we're going to learn how to multiply radicals. So what we're going to do here is when you multiply two numbers that have square roots, you're going to multiply outside numbers with outside numbers and inside numbers with inside numbers. So I would do the blue ones. 5 times 2 is 10. Now notice with the green, I got a pair of 3s. So again, if you remember when you made a pair, 1 comes out. Or you could do 3 times 3 is 9, and then you have to square root it. And then it becomes a 3. So this final answer here would be 30. So you could do 5 times 2 and get 10, and then you could do square root 3 times square root 3, get square root 9, but then you have to turn that to a 3. But again, it's a lot easier if you just know that when you multiply the same radical by the same radical, you get that number without the radical. You're making it a perfect square. Pretty good on 8. Let's keep on going. Number 9. Now, again, I don't want to have to do 5 times 5 and then times 9 and get 225 and then square root it. Now, some of you are going to realize that that's a perfect square. However, it's a lot easier to just say, oh, I got a pair of 5s. So a 5 comes out. And then here, you can either break this down into 3 and 3, or realize that 9's a perfect square. You square root it, and then 3 times 5 is 15. The square root of 225 is 15. Okay, so because we are not using calculators, you're better off factoring it, looking for pairs, and pulling them out, instead of trying to multiply everything. Because chances are, if you didn't know that 225 was a perfect square, you're going to have to go back and factor it anyways and do that whole tree thing again. So the same thing here. 11 times 44. This gives me 484. So again, after I multiply it, I still got to break it down. So it's easier for me to factor this thing. 11 can't be factored, but 44 could become 4 times 11. Now again, if you realize 4 is a perfect square, this becomes a 2. I got a pair of 11s, so then that becomes a perfect square. So my final answer here is 22. So actually 484 is a perfect square. It's 22 times 22. All right, back from our geometry days when we did those special right triangles and we had to rationalize the denominator. The rule is you can never ever leave a square root in the bottom of a fraction. In order to get rid of that square root, we need to make it a perfect square. And that process is called rationalizing the denominator. Now, in this particular case, just like before when we multiplied, if this is in a fraction, or think of this as division, remember how we could only multiply outside with outside and inside with inside? Same thing here. I can simplify this fraction, these two outside pieces, because what is 7 over 35 simplify to? 1/5, right? So I could make this 6 square root 1 over square root 5. Anybody know what the square root of 1 is? 1. Beautiful. So this just becomes 6 times 1. So now I have 6 over the square root 5. Again, I can't leave that 5 down in the bottom of my fraction. I need to rationalize this. And the way that I'm going to rationalize it is I'm going to make it a perfect square by multiplying the fraction by the square root 5 over square root 5. Because if you think about it, technically, this red square root 5 over square root 5, this is equivalent to 1. So technically, I'm just multiplying my fraction by 1, but it's getting rid of my radical in the bottom. So again, when we multiply, remember we got a pair of 5s here. So this really becomes the square root of 25, which is 5. But don't waste your time multiplying it. Just know that whenever you multiply a radical by itself, it makes the radical disappear and it frees up that number. Then the numerator, the 6 is outside, the 5 is inside. I can't multiply them together. I'm just going to sit them side by side. And there's your answer. So we can never leave a square root in the bottom. In order to get rid of it, we have to rationalize. And you rationalize by making it a perfect square by multiplying it by itself. Now, I could have started from the beginning and multiplied the top and the bottom by square root 35, but then I would have had a huge radical to simplify. So it's better to try to simplify before you try to deal with that. So let's try 12. So again, I'm going to try to simplify what's underneath here. What could I divide both of these numbers by? Good. Okay, so I could make this 5 square root 16 over square root 13. Because technically what I'm doing here is breaking this into 3 times 16 and then square root 3 times 13, and then the square root 3's cancel. So I'm sort of factoring it, but again, think of simplifying the fraction. Now, anybody realize what the square root of 16 is? 4. So I'm going to also fix that numerator up there, and I'm going to make it 5 times 4, and then I'm going to turn it into 20. So now I have 20 over the square root of 13. Can I leave my answer like that? No, I got to rationalize, right? How do you rationalize? What do you do? 13 over 13, right? Square root. So then now I can't multiply 13 and 20. I just put it side by side because 20's out, 13's in, and then the denominator just becomes 13. Now keep in mind, and we're going to see this coming up, if this part that comes out could be reduced, you need to do that. But I can't simplify 20 over 13, so I'm done. Next, we're going to multiply. So we're just using our distributive property here. So for 13, all I'm going to do is distribute the square root of 5 to the square root of 5, and then the square root of 5 to the 2. So again, when I multiply square root 5, I got a pair of 5's, so a 5 comes out. Notice when I do the next one, these are out and in, so I just write them side by side. So the number that's not under the radical, write first, and then the radical at the end. Sort of think that like the radical is a variable. Stick them at the end. Good so far? Yes?
Is that the final answer? Or
Yep. Okay, so because, and did we do any adding and subtracting yet? No. So in order to add and subtract radicals, this would have needed a square root 5 with it. So because this doesn't have square root 5, I'm done. I can't combine 5 minus 2. So again, think of the radicals like variables. So let's say it was this, 5 minus 2x. Can I combine those together? No. So think of the square root of 5 like an x. It's not a like term with that whole number. Okay, let's try. I had some at the bottom. Here we go. All right, so again, what we really should do here is multiply outside, 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 and then inside, inside, inside. However, if I do this, what I get on the inside is going to be huge. So what I'm going to do first is simplify each one. So the first one is good to go. I can't break down the square root of 2 anymore, so I'm going to leave that one. Then this next one in the middle, I'm going to break down the square root of 8. So I can factor this into 4 times 2. Everybody good on that? And then I could still break the 4 into 2 times 2. And I guess I'll just stay consistent because I've been bringing them all the way to prime each time. So now I got a pair of 2's. So one of those 2's comes out. I had a negative 2 out front already, and this 2 stays underneath. So now this becomes negative 4 square root 2. Now for the 27. So 3 square root 27. This one's going to break down into 3 times 9, and then 3 times 3. So I got a pair of 3's. So one of those is going to come out and join that 3 that's already there, and this 3 stays behind. So now I have 9 square root 3. Now, let's go back and let's multiply, I guess. So outsides, 3, negative 4, and 9. So all of those are going to get multiplied. And then under the radical, notice you have a 2, and a 3. Oops, we got a pair of 2's hiding under there. So in addition, I can also pull out one of the 2's. So now what I'm going to multiply is going to be the 3, the negative 4, the 9, the 2 that I just found hiding underneath there, and this 3 stays underneath. So now I'm going to multiply these 4 numbers, and I get negative 216. So negative 216 square root 3. This next one, I'm also going to do like I did before, and I'm going to try to reduce my fraction. Because technically what I could do here is say I'm rationalizing, but then I'm going to get too huge of a radical to break down. So instead, let me see if I can simplify the 6 and the 90. And I could actually divide 90 by 6. So I'm going to change this to a 15 and this to a 1. So now I have 15 times the square root of 1, which is just 15. And then now I have the square root of 15 on the bottom. Again, I need to rationalize. And I'm going to multiply the top and the bottom by the square root of 15. So this becomes 15 square root 15 over 15. Remember what I had said before, that if this could be reduced, you need to simplify it. So 15 divided by 15 is 1. So my final answer here is just square root 15. Yes. Okay, so now another one. Adding and subtracting radicals. So remember how I told you to think of radicals like variables? So sort of think of it like this. 8x minus 6x. Think of the square root of 3's like variables. What is 8x minus 6x? Beautiful. So the same thing's going to happen when you subtract and add radicals. In order to add and subtract numbers that have square roots, they have to be the same. If they're not the same, you can't add them. So I'm going to just do 8 minus 6 and then put the square root 3 behind it. So all you're doing is adding and subtracting the numbers in front. Now, notice number 17. They're not like. So you think, oh, I can't do anything. But what could we do to that 24?
Reduce.
Yes. So let's break that 24 down. So let's do 4 times 6. Now, if you realize that 4 is a perfect square, we could go right to 2 radical 6. Everybody with me on that? Or we could keep breaking them down till they're prime. So then this just becomes negative 4 square root 6. Now I have like radicals that I can subtract. So negative 4 minus 3 gives me negative 7 square root 6. So you always need to try to simplify the radical before you begin adding or subtracting. Same thing on 18. We need to break down that 45 and the 36. So for the 45, I can break this to 9 times 5. And again, if you realize 9's a perfect square, it just becomes 3 square root 5. Multiply it by the 3 that's already there. The 36, this is a perfect square. 6 times 6. So this just becomes 7 times 6. And then we would get plus 42. I cannot add those together. The 42 does not have the square root of 5, so I leave it alone. Next one is the same thing. We need to break 9 square root 5 plus 42. So the 42 doesn't have a radical, so I can't add it to the 9. Everybody good? All right. On the radicals first. So I need to break down the 32. Again, if you're good and realize that it's going to be 16 times 2, and realize that 16 is a perfect square, you could just make this 3 times 4, radical 2, 12 radical 2. The 63 is going to be 9 times 7, 4 times 3 times radical 7, and this becomes 12 square root 7. These are not like radicals, so I can't do anything else. I'm done. Again, think of the square roots like variables. Think of that as like an x and a y. And then here again, 12 square root 2 minus 12 square root 7. Next, we're going to be foiling. These are two binomials, but our binomials have radicals. So I'm going to FOIL. So first gives me 16, 4 times 4. Outside, 4 times negative square root of 11. Inside gives me positive 4 square root of 11. And last, notice I got a pair of 11s, so minus 11. When I FOIL these radicals, binomials, the middle terms should always be able to be grouped. Now we might end up with something, but whenever we have exactly the same numbers, and one's a plus sign, one's a minus sign, these middle terms here, the inner and the outer, are going to cancel. So really all I'm left with is first and last, and I get 5. This is going to lead us into our conjugates, where we have to get rid of a denominator. Let's try 21. It's a binomial squared. Again, don't think you could just square this and square this. We need to write this twice and FOIL it. So again, let me write it again. And then get rid of that. And now I FOIL. So I'm going to do first. And again, do outside and outside and inside and inside. So 3 times 3 is 9. Square root 7 times square root 7 is just 7. So this will become a 63. Outside, I'm going to get negative 3 square root 21. I'm only multiplying inside radicals. Then inside, I get negative 3 square root 21. And then finally last, I got a pair of 3's, becomes plus 3. Negative times negative. I now are going to go back and combine my like terms. Remember before when we did the other problem, these canceled. These don't cancel. Again, remember you only add the numbers outside. So the 63, rewrite it. The middle is now negative 6 square root 21. and then the end number is a plus 3. I can add the beginning, the two constants. So I'm going to add 63 plus 3. So final answer is 66 minus 6 square root 21. I cannot do 66 minus 6 because the 66 does not have the square root of 21. Number 22. Here's my situation where I have to rationalize. Can't leave a square root in the bottom. So in order to fix this, we multiply the top and the bottom by the square root of 2. This becomes 5 square root 2 over 2. And you're done. Okay, 1. Again, all we're doing here is rationalizing. So I'm going to multiply the top and the bottom by square root 3. This becomes 7. Remember, we only do inside and inside. So 7 square root 6 over 3. I can't simplify anything. The only thing that I could try would have been this. I can't do that outside 3 with the inside 6. Same thing on 24. I'm rationalizing. Root 3 over root 3. Now, what's different here is this plus sign. So this square root of 3 needs to distribute to the 4 and to the square root of 2. So this becomes 4 square root 3 plus square root 6 over 3. I cannot add that numerator because these are not like radicals, and I can't simplify anything. Again, that 3 that's in the denominator is outside a radical, so I can't simplify it with those things underneath. 2 more examples. I'm going to make it. Here we go. Okay, this is a little different. Don't think that all you have to do is multiply by the root 2. We have to do something different here. We have to multiply it by its conjugate. So what we need to do is multiply the top and the bottom by 3 minus the square root 2. I changed the sign. And now what I'm going to do to the denominator is make that square root of 2 disappear. I'm going to FOIL that bottom. So the bottom's going to become 3 times 3, which is 9. 3 times square root 2 is negative 3 square root 2. Inside is going to be positive 3 square root 2. And last is going to be minus square root 2. It's just going to be minus 2. Now, notice the middle cancels. So I'm only left with 9 minus 2, which is 7. For the numerator, 1 times anything is itself. So 3 minus square root 2 over 7. And you're done. Essentially, when you multiply something by its conjugate, all you have to worry about doing is first and last. And we have, yes?
It has to be negative.
It has to be the opposite sign. So the next one, see how it's subtraction? So my conjugate's going to be a plus sign. So it's opposite sign of what's there. Yes? So again, the conjugate is the opposite sign. So this was a minus, so my conjugate gets a plus sign. Now, this one I need to FOIL top and bottom. Now again, remember for the denominator, I'm going to just do first and last. That's all I need to do. So it's really just going to be 1 minus 2 for the denominator. And that's negative 1. But for the numerator, I got to go through the whole motion. I've got to do first and get 3, outside and get 3 root 2, inside I get 1 square root 2, and then last, root 2 times root 2 is just 2. Again, remember the middle terms can be combined, and so can these guys. So this becomes 5 plus 3 square root 2 over this negative 1. And then, it's 4, sorry. 3 plus 1 is 4. So 4 square root 2. And then I can distribute the negative sign to the top. And it becomes negative 5 minus 4 square root 2. Homework for this is due Wednesday.